My name is Emily Schoenfelder. I work with University of Illinois Extension in the Fulton-Mason-Peoria-Tazewell office. I work as a part of 4-H and the youth development educator there, and I am here today with Michelle Edgcomb-Friday, who is a professor at Bradley University, as well as my colleague Judy Schmidt, who also works for Illinois Extension as a 4-H youth development educator, and she will largely be running our tech today. So as we kind of continue to let people in and get started, I just wanted to find out how comfortable you are with implementing inquiry-based lessons into your classrooms or into your program if you're an out-of-school time educator. Judy's going to throw up a poll, I think, and if you guys would chime in and just let us know if you don't see yourself represented in any of those answers, feel free to hit Other and type into the chat and let us know more about that way. And we know we have lots of educators representing places all over the state, as well as different grade levels, different interest levels. So we just kind of want to gauge a little bit about your where you are with this. So we have lots of people chiming in. I don't know if you can see the results, but so far we have several people saying that they understand what inquiry-based lessons are, but are having trouble getting started. They try to use inquiry-based practices sometimes, but mostly for special projects or lessons. And you often use inquiry, but you're looking to deepen your knowledge on things. So that's awesome. And we will kind of try to gauge that. So I'll give you just another few seconds if you want to chime in and haven't yet. I think about 80% of us have chimed in, and then we will, if you're not seeing the results, we'll show those to you. Perfect. So I think that stands pretty standard. Lots of folks are having trouble getting started or use this already. So hopefully you can see the results and get to know that. So as we move on through this, a little bit about what our goals are. We are hoping that we can learn the benefits of inquiry-based education as we go through this, a little bit about the whys that we do this, understanding different levels of inquiry and how those might look in your classrooms, practice infusing inquiry or more inquiry into lessons that we already have, connecting that to NGSS, and then at the end, we're hoping that we can have some conversation around good resources that we have. Somebody says in the chat, I'm a recent graduate, so I don't have experience in my own classroom yet, but I'm looking forward to trying it out once I get a job. That's awesome. So as we move forward, can you go ahead and put in the chat box what you think of, or when you think of inquiry, what comes to mind? Like what do you think of when you first hear about inquiry? And go ahead and answer that in the chat. And I'll try and read out a lot of our answers in case we have folks who are traveling or listening to this in their car and not able to see the screen. Comparative questions. Student-centered, definitely we'll be talking some about that. Allowing students to explore and discover, project-based learning, exploring different ways to come to a solution for a problem. I love that. Science process skills, argumentation. That's a great point, using evidence to back up what you found. Exploration, student-driven educational experiences, using phenomena. And developing hypotheses around those, testing those, project-based learning again, investigations, exploring students' interest, that's a good one. Scenarios, tracking changes over time, guiding students as they teach themselves rather than spoon-feeding information. That's a great way to put it. Engagement, where their understanding is by questions, student-guided, inquiry leads students to develop their own understanding. Perfect. So those are all phenomenal answers and absolutely right. So here are a few definitions as said by other folks. So the Smithsonian Science and Education Center says inquiry-based science adopts an investigative approach to teaching and learning where students are provided with opportunities to investigate a problem, search for possible solutions, make observations, ask questions, test out ideas, and think creatively and use their intuition. And this one from the publication Inquiry in the National Science Education Standards says, from birth, children employ a trial and error techniques to learn about the world around them. As children and as adults, when faced with an unknown situation, we try to determine what's happening and predict what will happen next. We reflect on the world around us by observing, gathering, assembling, and synthesizing information. We develop and use tools to measure and observe, as well as to analyze information and create models. We check and recheck what we think will happen and compare our results to what we already know. We change our ideas based on what we learn. This complex set of thinking abilities, which helped early humans gather food and escape danger, constitutes the highly developed capacity we refer to as inquiry. And I think that that's a really lengthy definition, but I also think it's a great one because it talks about this is a human process, first and foremost, but also that it goes beyond just asking the questions and talks about how we're going to answer them and that kind of problem-solving skill, which a lot of you mentioned. So I'm going to go ahead and turn it over to Michelle to talk a little bit about why we do this.
All right. So when we're talking about why using inquiry-based practices, there are, as we all understand, pros and cons for any approach that you can take. And I'm not going to ignore what some of the trade-offs might be, but I want to start with what do we really get out of letting students explore and solve problems and answer questions. And, first and foremost, and this is going to kind of call back to last week if anyone was here talking about career education in the STEM fields, inquiry, better than any other mode of instruction, really represents nature of science and nature of engineering. That is, how do scientists and engineers actually approach the world and what do they do? So the nice thing is you get that chance to actively develop knowledge. And this is going to come up later again when we talk a little bit about inquiry and the NGSS standards, that developing knowledge is important. Very frequently, inquiry lessons really focus on reinforcing. You have standard teaching and then you have a kind of open-ended experiment. But if the students already know what the outcome is, it's not as deep of an experience. So you can develop concepts this way. You don't just need to reinforce them. You can have students really solving problems. And it doesn't have to be knowledge that's new to the world. It just has to be knowledge that's new to the students. Also understanding not just science, but across the STEM fields, how that information was developed in the first place. Another thing that came up last week in the career discussion was the exercise by which you introduce nature of science by asking students to draw a scientist or scientists. And I've done this exercise with kids as young as about 9. I've done it with graduate students. The pictures tend to be very similar. Grade school students are a little bit more likely to draw explosions. But I think what got me the most of all the times I did this was the college student who drew a stack of books that were labeled biology, chemistry, physics. And that's what inquiry is moving away from, looking at science as a static set of facts and rather looking at it as a way we have of understanding the natural world. This next one I want to emphasize too, because so often, at least for my students, I discover inquiry experiences are frequently enrichment. It's something that they do outside of their normal classrooms. It's they got to be on the robotics team, which is fantastic, or they got to do something else. But inquiry-based practices really kind of open the playing field to all students. One of the hallmarks of inquiry is if no one really knows what the answer is, it de-emphasizes the skills that traditional education can sometimes focus on. And it lets students who are not as good at traditional learning skills, but really stretch and have a chance to succeed. It prioritizes creativity and thinking through problems, and it's less focused on what you can, what you remember, quite frankly. And it's nice because it opens the playing field to more and more students. And this is one of the things that I kind of really like. When everyone's uncomfortable, that means everyone has a chance to engage. And that leads to the last thing that I really wanted to emphasize right now, which is that sparking interest. Again, we frequently ask students to display an interest in science and engineering out of the blue when they're older. Suddenly these classes appear when you're working into middle school. You aren't necessarily, and I mean, it depends very much on where you're at, but a lot of times by the time we ask students and really expose them to the STEM fields, they've already kind of got an idea of what they're interested in and what they're not interested in. But having these experiences where they get to figure something out, where they get to do it in a way where it's okay to be wrong, there's no one right answer, it's about trying to figure something out, can really open up the idea that, hey, this is not only something that I can do, this is something that I might want to do. And it gets that interest in science, in engineering, in other areas of academics. And then sometimes, you know, we kind of, we start seeing how math can be a tool rather than something that you're learning separately, and it reinforces all of those ideas. So these are some of the advantages. That said, and I'm very aware of this, inquiry practices generally emphasize depth over breadth. When you have 500 things you're trying to get through, inquiry takes time. We will talk more about this when we get to the next generation science standards and why it's important to not look at inquiry as something that's separate from or in addition to regular science education, but rather a means of doing science education. And it's also, it can be uncomfortable if you're not familiar with it personally. It doesn't necessarily reflect the science education that we all got. It doesn't necessarily reflect your college education where you're told to incorporate inquiry methods, and then you go to your science classes surrounded by 400 of your closest friends. It doesn't necessarily reflect what we saw K-12. If it does, great. I'm happy for you. It certainly didn't for me. And the more uncomfortable, and you know, there's research that backs this up. When we're branching out into things that are uncomfortable, when we're branching out into stuff that we haven't necessarily explored before, it's easier to fall back on traditional educational practices because they're safe, because you know what's going to happen, because you're not going to get questions that you don't know how to answer. So there are some trade-offs to inquiry, but I want to go back to that idea of opening the playing field. It's good to be uncomfortable because everyone learns that way. And when students see that you're learning and that you don't have all the answers, it makes it okay for them to be learning and for them to not have all the answers. That idea of being continually having a growth mindset. We're all still learning in this process. So it's a brief intro to why to use inquiry-based practices.
I love that idea of growth from discomfort. Thank you for that. So we are going to watch a video that's real short. It's about 5 minutes, but I want you to think about where you see those different aspects of inquiry that we talked about in the chat box and we read in the definitions, and then where you see the benefits existing that Michelle just helped us understand a little better.
So you think they like breathe through their skin or what?
When students are compelled to ask the questions that I'd want to ask them, but they're creating these questions on their own, that's when their minds are actually engaged. Do you see any sort of like respiration happening anywhere?
No, I do not. Oh my.
Here at the Springfield Renaissance School, I think if you step into any classroom, you're going to see a teacher who isn't lecturing, but really doing a balance of catch and release, student-centered learning. We begin with what do your lessons need to look like in order to make sure that students have a part in it. When teachers are designing a lesson, they're really thinking of what am I going to have students grapple with today? What am I going to have them figure out?
All right, so let's go look at some really gross bugs. I think if you overstructure a lesson, then you lose your students. Yeah, you might be really, really organized and you might tick every one of your boxes, but you lose them. So if I can be flexible enough as an educator to let them guide the instruction, that's where real learning lies. To start the class, the do now was to list the characteristics of an organism that you would need to know in order to determine its role in an ecosystem. Think specifically about the physical qualities of the animals, right? So what would you notice about it that would help you go like, this thing might bite me?
If there's more teeth or sharper teeth, they most likely eat like animals.
We shared out the list at the beginning of the class and created an anchor chart on the board of these characteristics that we would want to be paying attention to. All right, Gio, what are you thinking?
Way of transportation, or like its legs.
You're gonna look at some of these organisms and you're gonna be like, I don't even know which end is which. So if you get stuck like that, come back to the list.
We were looking for body size, the mouth, if it had legs or if it swam. The first station I was at, there were worm-like things, and they were like an inch long, each of them, and they were like tangled together and they were squirming on top of each other. It was kind of gross and awesome at the same time.
While students were off in their different groups, there was a level of intense curiosity.
Miss Fletcher, is there a reason why legs are in the front?
This is exactly what we're talking about, like those really weird body features.
Feathers on it.
I wonder what
think it has legs.
feathers. Okay.
I know, I'm not saying.
Tell me about that. And when I know that, like, yes, I've got them, is when they start asking the questions that I'm hoping that they would ask.
These like roly-poly looking ones, they're the isopods?
Yeah.
Okay.
If I'm not excited about what it is that I'm teaching, I definitely can't expect my kids to be excited about it. So if I'm modeling what it looks like to be curious and to safely investigate life, then they, I think, feel empowered to stand alongside me and do the same thing.
With Miss Fletcher, she's pretty curious, and it makes you want to go along with her and like learn with her, because she's only human, she doesn't know everything, so it's really fun to learn things with her.
Why are they moving?
That's a good question. Why wouldn't they move?
So that we can't see them?
Curiosity allows you to push yourself to understand more, to ask questions. It allows me to see for myself so I can have my own understanding of it. Because Ms. Fletcher, she gives you an understanding of it, but like when you see it up close, you can write your own notes and have like your own meaning behind it.
So this weekend for homework, what you're going to be doing with this information is hypothesizing what you think these organisms do in their environment based on the qualities that you are observing. I could have very easily just shown them pictures of the organisms and told them what role they play in the ecosystem, but there's not a lot of critical thinking that's involved in that. It's just sort of passive consumption. It's really hard to look at the mouth of a dragonfly nymph without getting really, really close to it, but they did because they were curious.
They can sense if prey is around.
So having all those little feelers out to be able to detect. They're asking the questions, they're finding the answers, and I'm just a facilitator. That's my job. And those are the moments that they take with them. And for an organism like that, why might that be important?
Because they're very small.
So do you think this is a prey animal or a predator?
This is definitely a prey. They would be.
Okay, so as we went through, you all had great answers, right? Like you talked about it being student-centered and student-led. The teacher was a facilitator, asking open-ended questions. The teacher's passionate, and everyone is using curiosity to kind of guide the lesson and guide questions. Student-produced anchor charts for use for categorizing, good questions. The teacher was involved with the activity. Everyone was learning together, being inquisitive, a diverse class of learners and engaged students. Those are all really excellent observations that you guys had. So thank you for that. And you're absolutely right. We want to talk a little bit about how we can kind of build this into our classrooms and scaffold this in order to be successful. So there are different levels of inquiry in the classroom, right? And Michelle touched on this a little bit, but there's kind of a continuum of what inquiry looks like. So at the beginning of this continuum, there's what's called confirmation inquiry, right? And that's the idea that students have the information, or a teacher has kind of presented information, and then they have an activity that just verifies that information, right? So the teacher provides the questions and the procedures for finding the answer, and the answer is kind of known by everyone already. So this reminds me a lot of like my high school chemistry lab, where the teacher would lecture, we'd get the information, and then we would go and follow kind of the cookbook recipe of how to put together an experiment or an example and come up with the results. And if it didn't show what we had already learned, we had done something wrong, right? So that's very much kind of confirmation inquiry, and that it's confirming what we already know. Structured inquiry is when you as a teacher provide the question and the procedure, but the students don't know the results yet, right? They're not quite sure what's supposed to happen, and they can kind of derive their own conclusions after following that set procedure. So for instance, if you were doing a unit on aerodynamics and talking about how surface area is related to drag, then confirmation inquiry, you might teach a lesson, teach the concepts, the vocabulary, the formulas if you're at that level, and say, okay, now let's see this in action. And you give students instructions on how to create different size parachutes. They test them, they record the data, and it confirms what they know. It verifies what they've learned. In structured inquiry, you might just flip that around, right? So you give the students the instructions on how to create these parachutes, they test them, they record the data, and then you ask students, okay, why did that happen? What happened, and why do you think that happened? So they're kind of coming to the conclusion by themselves. And so that is structured inquiry. The next step down the continuum is guided inquiry. So with guided inquiry, everyone has the same question. The teacher poses the question, but students have the opportunity to define the procedure for finding out the answer, right? They can come up with the method of how they're going to investigate that themselves. So that might look like a unit on density, and you have an activity where you have a tank of water and you drop into the water a can of regular cola and a can of diet cola, right? And one of them sinks and one of them floats, and you ask the students why, right? So you're posing the question, and then they have the opportunity to think through, okay, well, why is this happening, and how do I find out? You know, maybe they decide that they want to pour out the contents and make sure the volumes are the same, or maybe they need to look at it and see if there's any kind of visual characteristics that might be different. And maybe they eventually come to the idea that they're going to read the ingredient labels and see what might be different internally that causes that difference. So that's guided inquiry. And that's the first stage of kind of that, the more upper level of inquiry in the classroom. And the final one is called open inquiry. So open inquiry is when it is kind of entirely student-centered, right? Like the students are coming up with their own questions that they want to investigate and figuring out how to investigate them and figuring out what their conclusions are. So again, if you're doing density, right? So perhaps instead of you proposing the question, you might set out a lot of objects in tanks of water. So maybe you have an orange and a penny and a container, an empty plastic container and a ball of clay and a piece of wood, right? And you have students test whether they sink or float after making hypotheses. And then after they've done that, students can come up with I wonder questions, right? And those are a great way to kind of facilitate that questioning, that open inquiry. So I wonder what will happen if we fill the container. I wonder what will happen if we flatten out that ball of clay. And then you as the teacher facilitate those questions and help guide them through a process where they could test that, right? Sometimes they have really outlandish ideas that aren't feasible with the constraints of a classroom or the materials you have, and you can kind of guide and facilitate that into something that's more reasonable. But you help them think through those processes and those limitations. And you can also help them see connections they might be missing, right? So that's a lot of, that fear that they're not going to get the content we want. You can help ask those questions and help them see those connections so that they arrive at the information that you need them to have. So, within this, I want to emphasize that throughout this continuum, all of those levels are really important and have a place. None of them are a bad place to be. And in fact, sequencing those can really help facilitate the process and help your classroom become more inquiry-based. So it's a way to scaffold the students' skills and yours, right? So it can help increase your comfort level with it as well, because this is, as we talked about, it's really hard. And there could be a lot of barriers to creating a more inquiry-based classroom. So for instance, when you first start, you might get a lot of pushback from the students, right? That could be because they have no idea what you're asking them to do, right? Like they don't understand the process yet. It could just be because that's a lot more work for them, right? They're used to being having information handed to them, and now that they have to kind of construct that themselves, and so that can be like really hard for them to step into that role, or to feel like they have permission to do that even. And so starting at the confirmation level can help build those basic skills, right? They can start to learn how to make observations, how to record and communicate them, to learn the importance of replication of processes, and the list kind of goes on. But as you move through those levels, creativity is reignited. They get used to the idea that just because something doesn't work doesn't mean it's a failure. They can learn something from that. And so kind of going through the sequencing of those levels to help build those skills is really important. One thing I've noticed is that there is like an inquiry-based classroom is a little bit like managed chaos, right? Like, and that can be a lot worse if the students aren't used to it. So sometimes I think students equate the idea of having this freedom to explore and this freedom of questioning to freedom to do whatever they want. And so they, kind of lose it and behave like little animals running around the classroom, and that's not something that's conducive to learning ever. And so the sequencing kind of gets them slowly used to the idea that even though I am free to think and to explore, there are still rules in our classroom, right? We still have to behave appropriately so that it's productive for everybody to learn. And that, again, that process can be scaffolded. And another, I think, one of the biggest pressures that we have is that we are so pressured to hit the content, right? Like we have to hit every piece and, like we said, check all the boxes. And so the having faith that we can let go of that content-driven classroom and become more process-driven, that is really hard. And so you as a facilitator, if you can start at the confirmation level and slowly move up, it helps you to trust the process, to see it working, and to kind of learn, when do I start asking questions, or when do I let them guide the questions? When do I need to make these connections? Or when can they do that on their own? When do I need to start infusing the vocabulary, the formulas, the concepts, the theories, so that they know those terms and have that information? But when do I decide that they've kind of constructed enough of that themselves that it's safe to give them those facts without taking away from their learning process? And those are all things that you learn as you move throughout this process. So we are going to actually try to work on a lesson plan. Take a look at that lesson. You may have to download it, so I hope you're able to do that, or someone in the small group is able to do that. And think about, okay, what level, if any, of inquiry does this provide currently, and how can you adapt it to have more inquiry? And this could be that you are just slowly adapting the lesson plan as is to infuse a little bit more. And it may be that you throw out everything other than the learning objective and start from scratch. Like, you guys are free to brainstorm however you would like. I think folks are starting to filter back in. So what did you chat about? What did you notice? What did you think about? Feel free to type in the chat box or unmute and let us know what you talked about in your group.
Well, can I talk?
Please, yes.
Oh, okay. Well, in our group, we were talking about how you know, the presentation you gave us was very traditional and very content driven, memorization kind of driven, and we were talking about trying to make it more real, where the experience for the kids is more related to their environment, where they're at. It's more related to how, things they experience themselves when they learn the different aspects of it. You can do things where they experience it, whether it was the breathing or the respiration or the contamination. You can build models, like I would build models and test things like that. But wrap the whole concepts about solving a problem eventually, has to be dealt with, so that they becomes more personalized. So I think many times the way that is too abstract. It's always an abstraction that you just memorize short term.
Right.
You're done.
Yeah, absolutely. Thank you. Somebody said the lesson isn't inquiry. It was teacher-centered and only one word answers, one right answer. Yeah. We talked about how it was very teacher-led lesson plan. We talked about how kids that age are interested in how they're healthy, how they can play sports, how breathing helps their whole body. Yeah, absolutely. What else? Anybody else want to chime in via the chat or unmute and let us know? We'd love to hear from you.
Hi. So in our group, we were talking about how there was too much worksheets and not enough hands-on.
Yeah.
And we talked about how we didn't understand why the word scramble was in there. It didn't seem like it was very relevant. However, we really liked the visuals on that page.
Yeah.
And then as for the respiratory system, one of the young ladies had recommended that each person maybe a student or a small group becomes an expert in the other in a particular topic, and then shares out to the rest of the class. So there's like one person who has mastery of that.
Sure.
And then something else that we were discussing is how it's very relevant to COVID-19, and how maybe we could tie in a current event article with this. And then one of the other things we discussed was having the students create a respiratory system with a straw and a balloon, and possibly adding some material such as sand into the balloon to help them to understand the difference between what a healthy lung and a not healthy lung would feel like.
Right. Absolutely. Yeah, thank you. So more in the chat, we heard that we talked about how models and photos could help. Absolutely. Focused on vocabulary rather than concepts. It surely was. discussing how the lesson could be an introductory lesson to give basic vocabulary and information, but as the unit progressed, more opportunities needed for guided or open inquiry. Use this as an outline and give students to build a set of lungs, like we heard. That's awesome. We spoke about the different ways we could spark students to describe how breathing works using an activity. So a recommendation, as we heard, of a balloon and a straw. We did like how it started with what the students already knew. Absolutely, that was very cool. One of my group members mentioned making connections to their lives. So what's a system? What are jobs or functions of that system? But overall, the lesson was very teacher-led. It mentioned how we could talk about how it changed over time and worked on it. And I think somebody's raising their hand. Kathy, would you like to chime in?
Yeah, I think I mentioned a good introductory lesson because they do need that basic knowledge of kind of to start. I think the inquiry, the guided and the open could come with the big question of why.
Mm-hmm. Yeah, absolutely. Yeah, thank you for that. It was recommended, somebody said it was recommended to use a sponge to imitate the process of how lungs absorb and change depending on the environments. I love that. And I know, when I read this, I thought a lot about, oh, Kathy, I'm so sorry. Did I interrupt you? You cut out for me.
You're fine. I was just saying, getting to the why, so then the students start to question, why would we want to know what's good going into the respiratory system? What things out in the environment are good and what are bad, and how can we start to make some changes, and those sort of inquiry questions that lead the conversation. This is something that they need to know, but it's not inquiry based, but it will easily lead to some inquiry based questions.
Yeah, absolutely. And thank you. And I apologize for cutting you off. You stopped and my computer, right as you said, we need to ask why. And I thought that was the end. So I apologize about that, but those are all excellent questions. Thank you so much. When I was looking at the lesson, I was trying to think how you could keep the basis, like the bones of that lesson, and thinking sometimes just swapping them, what they asked, instead of saying like, here's a picture of a healthy lung and here's a picture of a smoker's lung and here's a picture of a miner's lung, just put pictures up and say, what do you think is happening here, right? Like what could have caused that? And start to ask those beginning levels of inquiry just by kind of flipping some of the lesson around. Michelle said this is a good example of where the lesson can really be expanded simply by removing an example and asking a question. Exactly. For example, what in the air might affect how you breathe? Yeah. So thank you all for that. Those are all fabulous brainstorms and inputs. One more, I like doing a little exercise with breathing in and out, the application first. Discussion is very important, and you hope it sparks some questions. Yeah, that's fabulous. So you guys have such great ideas, and I appreciate you for being willing to share them on here. But I'm going to turn it over to Michelle again, and we're going to talk a little bit about NGSS.
Okay. So we've already been talking a little bit about how to connect inquiry to what we teach and how to expand. And I really like the example of the lesson we just did in the breakout groups, because there's a lot of, when I'm working with my students, I talk about shifts towards inquiry. How can you take something that is very scripted and with things that are even small changes, when we're getting into this and we're really not, we have different levels of comfort and we have different levels of experience. So there are a lot of times where you can take a lesson and do something as simple as taking away the data tables. So students have to figure out how to collect that data on their own. It's a very small shift, but it brings students into the game. And when we're talking about how inquiry fits into the NGSS, short answer, permeates. I don't know how many of you were familiar with the Illinois standards before the NGSS shift, but back when we had the old Illinois learning standards, inquiry was very much part of it in goal 11 that was all basically on science process, but it was separate. And it kind of fit very well with what we might think of as the traditional representation of the scientific method as we have here, where you have something that might be iterative, ask a question, test it, revise your ideas, but is largely linear and set up in a way where there's a set process that you go through. First you observe, then you ask questions, then you form hypotheses. And this is a kind of a classic model, but it's very limited. It implies that there's really only a single way that scientists work, which is not true. It makes it what is normally and frequently a very start and stop, creative problem solving kind of process, which came up in our small group. It makes it look very linear in a way that it rarely is, and it doesn't include engineering. So all of these were and the way it was set up, where you had goal 11 was the inquiry process, goal 12 was based more on concepts, and goal 13 was more of a little science and society kind of. It made it very easy to make it be, okay, we're going to do the one inquiry lesson and we're done. And then we can focus on the content, which isn't the way it was really designed to be. Emily, can you advance? Can I advance? I'm not sure how that works. Thank you. Okay, so what the NGSS really did was it tried to shift away from that standalone model where inquiry was separate from concepts. When you look at the Illinois standards now, which are the NGSS, everything is designed around three separate, I shouldn't say separate, it's three connected concepts. The practices of scientists and engineers, disciplinary core ideas, and cross-cutting concepts. And every performance expectation includes all three. And that's deliberate. It's designed to make sure that looking at how concepts fit together across disciplines and how we figure out ideas are used to build the core concepts. It isn't meant to be discrete, separate things. It's all meant to be something you bring together so that students are learning those concepts through engaging with them. And the other thing they switched is they went from talking about science methods or methods of science to rather practices of science and engineers. So the goal here is to understand that there are a lot of different ways to think that you have to tie in to approach engineering problems or scientific questions. So the traditional scientific method is still part of it. It's the kind of thinking that we can think of as an investigation model that is deductive. You start with a general idea or a hypothesis, you make specific predictions, and then you try to test those. And it's not saying that that isn't still important. It's just de-emphasizing that that's the only way to process information. There's also the concept of developing explanations. An inductive process equally is important. If a hypothesis is going from a general idea to a specific prediction, how did you get your hypothesis to begin with? Chances are you were using inductive reasoning, which is equally important. You are taking your experiences and your observations and your ideas, and you are trying to make sense of them out of a general idea that could explain, that could offer some explanatory process, some explanatory power. So developing explanations for what you're seeing is equally important. And then on both sides of this, in the middle is going to come with your evaluation. How do you know if you are supporting your predictions? How do you know if your hypothesis is reasonable? Can you take that information? Can you analyze Can you come up with better ideas? Can you critically think about what you're observing? Can you critically think about the data that you have? None of this is linear. We move back and forth from these three domains on a regular basis. And there's a reason that that analysis is in the center in this model. We are constantly using that analysis and feeding back out into the outer ways of thinking. And the NGSS really emphasizes this as what it means to be a practice rather than just a method. A method is an algorithm. You can memorize it. You can do your checkbox. Okay, I've made my hypothesis. I've collected my data. A practice is really focusing on what do you need to continue to keep doing to make your ideas better. All right. Okay. Next slide. I think I've got one more. All right. That being said, these practices are designed to inform everything that every disciplinary core concept and every cross-cutting theme within the NGSS. They're all designed on how do you tie any individual idea to a broader picture. They're all designed on how do you figure out the concepts to begin with. And they have a list of, rather than again a single method, they have a list of the practices that are common to science and engineering. I broke it down into a little bit of a Venn diagram to kind of get to the question of how do scientists and engineers approach things differently, because we really do. There's a lot in common between science and engineering, and everything in the middle is meant to indicate that. All of these are practices is listed in the NGSS. All the ones in the middle, scientists and engineers are going to look at very similarly. You know, how do you develop and use models? How do you plan and carry out investigations? What's a little bit different is the overall focus of what your driving interest is or your goal. It's not that, so I have science on the left, engineering on the right, science more of a focus on asking questions and constructing explanations, engineering more on defining problems and designing solutions. This is reductive. I get it. I'm not trying to say that scientists don't try to define problems and figure out solutions. And I'm not trying to say that engineers don't ask questions. They do. But if you're really looking at philosophically what separates science from engineering, this is one way to kind of look at that and approach it. Because while the tools in the toolbox are very, very similar, we don't necessarily process things in the same way. There is a reason that ultimately these are different disciplines. We do approach things differently, and we think about things differently a little bit as well. And so this is kind of a way to take a look at it. And one of the things that I also kind of wanted to stress, if you look at the NGSS, there are actually more cross-cutting concepts now than there were when it was first implemented in Illinois about 6 years ago. I think 2014 is when Illinois officially adopted the NGSS, in that it also is starting to ask us, how do science and engineering connect to each other? Which is another reason why I kind of like having the Venn diagram approach, to start looking at what are our commonalities and what does make these approaches distinct. Okay. Comments or thoughts or questions?
I know when I've done this in the classroom, that engineering aspect, I've focused on that more and more lately, over the years, trying to get the kids to solve a real problem. And they learn this, like in physics, where we learn the concepts of physics, but then they got to build me a car that's really fast, and you know, the faster the better. And so it comes down to solving like a practical problem, and that's engineering. You know, they can learn about the theories of motion, you know, in physics, but when you apply it to solve a problem, that becomes engineering. And I think the two really work well together. At least for me, when I teach the hands-on, what I've taught in high school and now I'm teaching in middle school, that's where I really hook the kids and get them engaged, is when they try to solve the problems doing engineering. I don't know. I mean, I have an engineering background, so it's kind of easier for me, but I really think the engineering adds quite a bit to the curriculum.
Yeah, thank you. What other questions or comments do you have? Feel free again to chat in the text box or to unmute and ask our questions. And once we've wrapped that up, we'll go back to the resources slide and we'll send all of those out as well. But I'd also love to hear any resources that you all use that you found helpful in kind of implementing this. Question, any suggestions about continuing inquiry-based learning if we have periods of learning again? Oh, periods of e-learning again. That is a great question. Michelle, do you have thoughts on that?
Yeah, I do. So I think a fair amount of this, I think a fair amount of this depends on what grade level you're teaching. That's not to imply it can't be done at all grade levels, just that it might look a little different depending on where you're teaching. One thing that there are a couple of different ways to do inquiry lessons when you are not face-to-face. One is to focus on things that can be done with household products. And this, again, this is where the age range is really going to matter quite a bit, because the amount of adult supervision and help that they're going to need is going to vary a lot. And I do want to put that out there. But there can be a fair amount of what can be done in a classroom that with some amount of instruction and supervision you can do at home with stuff that is reasonably likely to be available. Another thing that can be done is, and this would require less adult supervision, which is kind of nice, but you can focus on question development and having your students all contribute to how you can test something, that then as an instructor, you can set up the test yourself and take pictures or record and do those kinds of activities. The downside is the kids aren't getting as much hands-on, but you're still emphasizing a lot of the thinking skills that goes along with inquiry work. So if you're going, and it can still be something that you focus on household products. Incorporating video is another way to do that as well. It's not ideal. It's better if you can be hands-on, but it at least can be a little bit more of a stopgap measure where you can have videos that students are watching and that they're analyzing and critiquing. And if we're looking at that kind of model of your deductive, your inductive, and your analysis in the middle, there's a lot that can be done with that analysis portion that's still kind of fun. And sometimes there are things that you can come up with that, depending on what you're trying to answer, stuff that you can get self-data from. So going back to the lung experiment, if you're trying to figure out things that make your respiration rate increase or things that make your heart rate increase, or trying to decide, you know, which has a bigger impact on your cardiovascular system, doing something like running versus jumping jacks, you know, that's the kind of stuff that kids can measure on their own. And there's a lot that can be done with, especially if you're doing physiology, if you're doing any kind of biological function, there's a lot that can be done with self-data. Those are just a few ideas.
Could I also add on to that? My school was lucky enough to receive a participation through Boeing this year, and they did something called student learning buddy systems. They did family, I can't think of the words, but they did family projects, school projects, and then they did STEM night. And what we did with the family projects is basically we prepared the materials and put them in Ziploc bags and then sent them home with the families. So if we're still in remote learning, if I was going to do something, I was going to give the option for the parents to buy the materials themselves. But if they can't, possibly having them at the school for them to pick up, so that you can have them all getting that hands-on experience without having to be there, and possibly having them do it as like a family project.
That's a great idea. Thank you. Someone responded in the chat box, spaghetti bridges design and testing. That's a great one, easy with at-home materials. And on the resource side, Kathy said Wonderopolis is a fun website for students to read information articles on all sorts of topics. So you use it to, or she uses it to introduce the phrase I wonder, so that students can get used to asking those inquiry questions. That's fabulous. Thank you. Any other questions or resources that you all would like to share?
Thinking about things that are easily available, even more technical things like water test kits, the kind of dip and color change things frequently can be purchased online, even through places like Amazon now. That way you're not worrying about sending chemicals home with kids. Yeah, clearly. If there's a ton that you can explore, both chemistry-wise and things like biological membranes, with some vegetable oil, some water, and some food coloring. You know, just very basic things. So I do like that. The idea of making prep kits and sending home is a great idea, and a lot of it really is. I know budgets are incredibly tight right now, so. Emily, I've got, if it's okay with you, I'll post the link to the video of the second grade motion. Okay.
That would be
and I'll just put it in the chat box.
Perfect. Yep. And we will include that in the resources.
Okay.
And just the ones that are up, and these are certainly, this certainly isn't a comprehensive list, but Illinois State University has the CMAST, and they have very inquiry-based curriculum that is available for free to educators. Edutopia is where I found the video that we watched today and has great information. The video that Michelle just posted is so exciting because it talks about local teachers and how that they are incorporating it, especially in some of the younger grades. For anyone who's an out of school time educator, Click to Science has great resources for activities that are sometimes kind of after school type activities or just single activities when you're not kind of building a curriculum. Of course, the National Science Teaching Association has great information on NGSS and good curriculum planning tools for that. And Just Science Now has examples of inquiry-based lessons at those different levels that we talked about. Oh, thank you. I'm sorry, Michelle. The Center for STEM Education at Bradley also has classroom kits that can be checked out that you can use, as does 4-H. So feel free to contact us for those as well. So thank you all for joining us, and have a great rest of your week.